Welcome to Lesson 4 in Basic Calculus, the derivative of a function and the slope of the tangent line. Get ready with your scientific calculator, pen and paper as we discover further the relationship between the derivative of the function and the slope of the tangent line. To start, recall that the slope is the ratio of the vertical change to the horizontal change. Now consider the function g of x equals 4x minus 2.
Now to get the slope of the line, we have get the difference between the ordinates over the difference between the abscissas. Simplifying this, we will have negative 8 over negative 2, which is equal to 4. Now looking at the function, we have g of x is equal to 4x minus 2.
Recall that in the slope-intercept form, y equals mx plus b, m is the slope of the line. Hence, in the function g of x equals 4x minus 2, m is equal to 4. That confirms our answer a while ago, using the formula of the slope, that m is equal to 4.
Now what if we are asked to find the slope of the curve? Before that, let us define first some terms that we will be using during our discussion. We call that line that intersects the curve at two distinct points as the secant line, whereas if there is a line that passes through the curve at exactly one point, we will have a tangent line. And the line that is perpendicular to the tangent line is called the normal line.
Now let us discover how the derivative of the function and the slope of the tangent line related to each other, and how the slope of the curve related to the slope of the tangent line and the derivative of the function.
In the previous slides, we have recalled the process of getting the slope of a line, which is the ratio of the vertical change over the horizontal change. Can we still use the same formula? In this case, if we would be able to determine a line that is tangent to the given function, then probably we can estimate the rate of change in y with respect to the rate of change in x in the given function. Let's have point P, and there is a line that passes through that point, and let's label that as line L. And then we get the coordinates of point P. Now, since this is just an arbitrary point, then it will have an abscissa of x and an ordinate of f of x. Now let's get another point on the curve and label that as point Q. Point Q will have an abscissa of x plus delta x and an ordinate of f of x plus delta x. In other words, it will have coordinates x plus delta x, f of x plus delta x. Now what is this delta x? Delta x is the difference between the abscissa of the 2 points. Okay, now let us draw a line that passes through these 2 points, PQ. So we have secant line PQ. Now what if point Q will slide down to point P? Then delta x become arbitrarily small, and note that the slope of the line PQ will be closer and closer to the slope of the tangent line.
Note that point Q may be located at the lower left of point P.
So it's like getting the limit of the function as x approaches the given point. Now let's recall how to get the slope of a line. Okay, the slope is equal to the change in y over the change in x. Using symbols, we will have m is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Then we will have m is equal to our y sub 2 is f of x plus delta x, since that was the second point. Then our y sub 1 is f of x over the x sub 2, which is x plus delta x. And then our x sub 1, which is x. Simplifying this, we will have f of x plus delta x minus f of x all over delta x, since we can cancel this 2x's here. Now remember, we would like to make delta x arbitrarily small. So we set delta x approaches to 0, since point Q may be located at the left or at the right of point P. In that case, we are dealing with the limit of the function. So in other words, to get the slope of the curve, which is just the derivative of the function denoted by dy dx, is equal to the limits of f of x plus delta x minus f of x all over delta x as delta x approaches 0. So in other words, the slope of the curve, the derivative of the function, and the slope of the tangent line means the same thing.
Formally, the derivative of the function f is denoted by dy dx such that its value, the number x in the domain of f, is given by dy dx equals the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0 if this limit exists. So this means that the function will have a derivative only if the limit of the function exists. The following are equivalent ways of writing the derivative of y equals f of x. First, we have dy dx. The second one is read as y prime. The third is read as f prime of x. And last is read as the derivative of y with respect to x.